Hi all, hope all is well. On today's video, I'm hoping to explain the next experiment that I'm hoping to complete. Lately I've been working with seawater quite a bit, and out of interest I wanted to see exactly what would happen if I was to use electrolysis to actually process the seawater. So recently I've been working a lot with the power of the sun to actually desalinate the seawater so I can extract drinking water from it and to leave the salts behind. And I've done it in a different couple of processes. One process was using an air still to complete it, which was successful. I think I got 3.5 litres of water to 150 grams of salt. There was a bit of loss as well. And then I've recently been doing quite a bit of work with the jar experiment. So it's just 2 jars, one inside the other. The inner jar has salt water in it, and through the process of leaving it in the sun, the light interacts with the surface of the water, knocking off molecules of water. During the night it condensates, and then you extract the drinking water through that procedure. Now, what I've known for quite some time, and it has been done, I'm definitely not the first person to try this, but I do want to try it for myself just so I can learn from the experiment, and that is to produce a H cell. So what you can see here in front of you is an example of what a H cell would look like. Now I've drawn this up myself, so it's pretty basic, but all the information's there. The way it works is you hook up a solar panel, as you can see here, back to a battery. From the battery over to an anode and to a cathode. Now what you can see here is 2 jars, and they're just going to be 2 plastic containers, and they're going to be joined together with a piece of plastic tubing. Now it's going to be completely sealed off so there's no leakage, and then in the middle of the tube there will be some cotton wool inserted, and that acts as a barrier to stop the 2 liquids interacting. Now in each of the liquids, it is going to be just plain seawater. So it's seawater I've collected from down on the beach, and in both of them will be exactly the same. The only difference will be is that one will be connected to the negative terminal of the battery, and the other container will be connected to the positive terminal of the battery. And the idea of that is so that when I connect these terminals up here, these are carbon rods that will be inserted down into the water. Again, they will be completely sealed off, so there's no escaping air, no escaping gases from it. And when I turn it on, what will happen is the electrolysis process will actually generate an electrical current through the gap here, through the tubing, and to the positive. So there'll be a current discharged through, and it will return back to the battery. And when it does that, it will actually break the salt water down. And when it breaks it down, because there's 2 separate jars and they're separated by a membrane, which is the cotton that I'll be inserting in here, you'll get 2 separate products from it. One of the products will be sodium hydroxide, which can be used to make soap, and is actually used to make soap today. That's how they produce it. There'll also be hydrogen produced. So up the top here, there'll be 2 ports on both jars where the gases that are generated at the electrodes will escape and fill balloons. That's the plan anyway. I don't know how successful that will be, but we'll be all there to watch it together and probably get a good laugh out of it. Hydrogen's very explosive, and I do plan on blowing some up, which will be awesome. Probably get the police around pretty quick. And then we've got oxygen being produced over here. So you can use this to produce sodium hydroxide and the hydrogen gas. The hydrogen gas itself is actually a fuel. Sodium hydroxide, that's what I'm really interested in. I want to see how much sodium hydroxide will actually be produced out of so many litres of seawater. I'm not sure exactly how many litres of seawater there will be just yet. That's to be determined shortly. And on the other side here, not only will there be sodium hydroxide produced in this side, but in this one over here, there will be chlorine produced. And chlorine's extremely valuable as well, of course. And it can be used to purify your water and stuff like that if you ever get stuck. And overall, it's just a very interesting process to learn, and I was hoping to share it with you. So at this stage here, there are a few separate things you'll need to do. It is very basic. You've just got to put in the effort to actually get the gear together to do it. The actual process itself is just called a H cell. It's electrolysis is a process. It's an electrolytical cell basically, and it was invented by Alessandro Volta. He's the scientist from the 1800s who is credited for inventing this procedure. However, if you go back through ancient history, there are examples of some cells made out of clay pots and that date back into 2,000 years, stuff like that. So they're called Baghdad cells. They're not too sure exactly how they work, but rest assured, Alessandro Volta, he may have been credited for actually patenting this procedure, but he may not have been the first person to actually have invented it. It's very likely someone else come across it some time ago. This is done on a large scale today. So basically you get factories set up next to the ocean, and when they set up next to the ocean, they do exactly this procedure on a grand scale though. So they produce sodium hydroxide, they sell it. They produce chlorine, they sell it. They produce hydrogen gas, they sell it. And oxygen, you can actually use that in your breathing masks and stuff like that for your hospitals. So this procedure here, if you can understand how to do this, you can use this to do a lot more things, yeah. And some of the things that you can do with it, instead of using seawater, you can use molten salts, for example, and you can extract pure sodium or pure potassium from it. And those elements you have to keep under wraps, so you have to keep them under oil. As soon as they're exposed to the air, they'll explode. And eventually, I hope to be able to perform some of those experiments myself, although it definitely won't be doing it in town here. Now, I'll quickly run through exactly what it is that I've got going on over here. So that's obviously the plan, and it's very basic, but all the information's there. If you have a look down here, you can actually see that I've already got the panel set up, and the panel is hooked up to a charge controller up under here, and from the charge controller it runs along this cable here back to the battery. Two connections, positive, negative, and that's charging the battery. It's keeping a consistent current running through it as well. And then from the battery itself, I'm running back to 2 points here. So I have a negative clamp and a positive clamp, and that's what I'll be connecting my anode and my cathode carbon rods to, which is these items here. So that's my power source. The only thing left to do is actually build the H cell itself, which I'm about to show you how to do that as well. Okay, so to make a H cell, you can go about it the cheap way, which is exactly what I'm going to do. You could consider purchasing one online. Now there are several H cells available online. I did have a look. You can buy them outright. They're quite expensive though. They're made out of the same glass that Pyrex is made out of, so it's a borate glass, and it is quite expensive, so it'll set you back at least several $100s to buy a H cell. Now of course, once you've got the H cell, you've got it forever, and it's probably a really good investment, especially if you're looking at doing it on small scale. However, I'm going to go to the trouble of exactly explaining to you how to make one for yourselves. So the way I'm going to do it is quite simple. Went and purchased a couple of cheap sealable containers, so they need to be able to be sealed from the top, and these are like 2.3 litres each, so I guess that's what I'll be working with. I'll probably work with around 2 litres of seawater in each, so it'll be a 4 litre mix in total. You're going to want some balloons, so a couple of balloons each, one for each. You're going to need plastic tubing, which I was fortunate enough to get. That's going to actually be the bridge between it, so that's going to get installed in there like that. You're also going to need some glue, so epoxy, so you can seal it up. You're going to need a couple of extra pieces of the tubing that will go on the top, and then the balloons will be installed on the top like that. Again, they will need to be cut to fit, sealed. A bit of duct tape as well, so you can actually tape the balloons onto the tubing, because as the gases expand, the balloons will fill. That's the idea. So one will be full of oxygen and the other will be full of hydrogen. And we're also going to need some cotton wool. So this here is just going to be a pad that we're going to tear to pieces. It's a makeup pad, and that will be stuffed inside that bridge there. You're also going to need a couple of carbon rods. These aren't as difficult to come by as what you think. You can literally walk down the side of a highway and find a 9-volt battery. You can actually just pull the battery to pieces. So it's a battery that's out of an old torch, big square batteries. I don't know if it's a 9-volt battery, but if you find the old torch batteries, they're about this high with the springs on the top. You can actually break them open and you can get your carbon rods out of them. So we need 1 carbon rod for each, and that's where we'll be plugging our electricity into. And other than that, you're going to need literally a pen and a knife to cut the tubing in, and that's about the extent of it. Of course, you will need your car battery or a battery of some sort. This is just an old car battery that failed. However, if I hook it up to a solar panel, I can still generate enough electricity off it to do my experiment. You're going to need a heap of connector cables as well, as you can see there. You're also going to need the solar panel, which I've got there. However, if you don't have the solar panel, just using a car battery by itself will be more than enough, providing it's full, of course, because you will be discharging quite a lot of electricity through this system. And that's about the extent of it for everything you need. So you can see here I've got the solar panel clips that run back to the solar panel, and then this is the separate cable itself as well. So this cable here, I just made this up before. It's just 2 sets of clamps, so it can go from the positive to the positive on this container, and the negative one will run back to the negative one on that one. When I make that connection, the last connection, this one here, that will be the final connection, and then the cell will be activated. Once it's activated, things will happen very quickly. I don't know exactly how long I need to keep it on for yet. I guess once these balloons start inflating and they look like they're about to explode, I'll probably just pull the plug on the experiment, and then I can test my results to see how much sodium hydroxide has been produced in this one and how much chlorine has been produced in this one. From what I've read online, there is only a minute amount that is produced. I have done this experiment in the past and I have seen the results. It's quite obvious to see the results when you get the opportunity to have a look. You can actually see a white sediment forming in this one, and the water in this one will turn slightly green from the chlorine. That's from what I can remember anyway. But other than that, I guess it's probably time to set this camera up and struggle to try and build this H cell. First thing you're going to want to do is just mark these up. We just want a basic idea of where we're cutting. I know under normal circumstances things would be a lot more precise, but this is a backyard operation and I can do pretty much whatever I want. Just like that. And you're also going to want to do the bridge as well while we're at it, so we just want to put that roughly in the middle like that, and from that we can mark that up, which is not as easy as it looks. Then again, nothing ever is. And you want to make it as tight fitting as possible. The tighter the fit, the less glue we're going to have to use on it, which is always a bonus. And this one over here, we want it to rest in there as snug as possible, so somewhere like that. Like so. And then we want to put the last one up here as well. Doesn't matter where it goes, although it would be good to try and make it symmetrical, I guess. That's going to join like so, and that one's going to be at the back here. We can put this one up here. Just like that there. Now we will need to be inserting our carbon rod as well, so obviously our hose is going to go in there. carbon rod will go on the opposite side, so somewhere like that there. We want to make sure that we don't interfere with the bridge if we can help it, but I think that should be fine just there. And here comes the cops. That was meant to be a joke, but it's a pretty crap joke. And just like that. So that's where our 2 electrodes will go. Pipe will go up in there as such. And that should get us started. And if we can get this done and it's a nice snug fit, we should be able to glue it up, and within say half an hour it should be ready to actually fill up full of fluid, and we should be ready to proceed. And the worst part of doing this kind of stuff is it's a one-way ticket. Once you bust a hole through this, it's pretty much game over. So you've got to get it right. And look at me go. And that did not work. Now, as you can see, I've cracked it, so I did a fantastic job on that, which basically means I'm going to have to go about this a different way, which is going to involve getting a drill and drilling the holes out, which is probably what I should have done in the first place. However, I thought this plastic would be a bit more pliable than that, a bit softer, not quite as brittle, but it's all a learning curve. We're all learning together. It's great. So we're going back to trying to drill the top of this. We're not going to try and cut it because apparently that didn't work. That will be an easy fix, so I can just glue that back up. However, when it comes to measuring for your carbon rods, you just want to size your drill bit up. That there's slightly smaller than what the carbon rod is, so that should do fine for that one there. We'll give it a crack and see if we can't crack this lid just like I did before. Makes for entertaining viewing, I'm sure. And that is pretty close. I should be able to just shave the dimensions off that. Just shave a little bit off the edges, and I should be able to squeeze that straight in there. Add a bit of glue, we'll be good to go. As for this bigger one, I'm going to use a series of smaller holes around the outer edge, and then I'll shave it using this knife. That's the plan anyway. That's it. It's a pretty neat fit. It needs to be cleaned up. That's it, that's what we want. Except not that piece. This little piece. So, just have to use a bit of glue on that crack, which is a bit sad, but that's the way it goes. I'm never going to get over it. Okay, now to cut the bridge hole. Now if you were a bit more organised, you could easily purchase a hole saw to do this, and you would save yourself a lot of dramas. The only thing we need to do now is just cut that one remaining hole into there for the carbon rod. And then we need to glue this up. We need to glue all the fittings up around the edges here as well. Once that's done, we can glue the bridge up here. We need to actually put the cotton wool inside there as well. Now that was pretty much a bit of a disaster trying to complete that. We did crack the lid, but all is not lost. It did end up working out alright. So obviously I've still got to glue all this up, but as you can see, the carbon rods have been installed on both sides. That's where our electrodes will be connected to, and then back to the battery. And then we have the balloon holders here as well. So these are the vents, and the balloons will be installed on the top of these, so that when the gases escape from the electrodes and from the seawater itself, the hydrogen will be produced on the negative side and the oxygen will be produced on the positive side. So that there is exactly what we were chasing. So it's turned out exactly as I had planned so far, except for that crack, which really sucks, but that's the way it is. Anyway, we'll keep cruising. We'll glue her up and we'll see how it goes. Okay, and before we proceed with gluing this up, you're going to want to clean all the shavings out of it. So there's plenty of shavings in there from actually going ahead and drilling that. Once they're removed, all the contaminants will be removed from it, and then we know for certain that when we put our seawater in there, there's no other contaminants in there to interfere with the chemistry of the experiment. Okay, so now that we've cleaned all the shavings out of it, you want to make sure that you dry it all up, of course, because we're about to use adhesive onto the plastics and you don't want any moisture on there while you're doing that. Now it's just a matter of assembling the device back to where it was and then using the adhesive to seal the unit up completely. As you can see, I've completely reassembled it back to where it was. This time there's no shavings in there, so that's a bonus. And everything is set to the dimensions that I wish it to be. So as it is there, I should be right to use adhesive now to glue the unit up. Now the unit has been completely glued up. So I used up everything I had, and then I had to go back to using silicone as well. And what I'll do is I'll let it dry completely, and then once it's completely dried, I'll actually go ahead and put the cotton wool back inside the bridge here as well, and that will be the membrane for the device. Once that's done, what I'll do is I'll fill it up full of water, and once the unit has been filled up full of water, it can be completely tested for leaks. And if there's any leaks, that's when we can use the silicone just to patch up any leaks in the device. And once the device is fully sealed up, you can go ahead, put the seawater in it, and then we can start the experiment. Alright, so this has had all night to sit and to set. Basically, yesterday I had taken the time to completely seal the unit up. You can see the glue and the silicone throughout the entire contraption. I also sealed it up from the inside out as well. So as you can see up underneath here, use silicone to seal that up, and around the actual bridge as well. So all the way around the top and around the underneath as well, up underneath there. And by doing that, I'm hoping I have completely sealed the unit up. Now there's only one way to test that, and that's to actually go ahead and fill it up full of water and to see if there's any breaches. If there's any leaks, we need to go ahead and seal them up. And as you can see, by filling the one container, both containers fill, and there's no breaches. So there is absolutely no water leaking out of that, which means this will be successful. Now it's just a matter of putting the seawater into the cells and then hooking the system up. And there is a way to test the top release valves and that as well, to make sure that everything's sealed up, along with the carbon rods as well. And all it is a matter of blowing a bit of air into one port, and if it rises on the other side, then it means that we're forcing the pressure in. It's holding its pressure, forcing the water to rise. So we'll give that a crack. Which you can see there. So it should be successful. Now, one of the biggest concerns I had when doing this was exactly how long it was going to take to do the reaction. So I was still uncertain about exactly what the ampage would be that crosses from the negative to the positive terminals. So how much power is it going to consume to do it? And the secret to that is actually the width of the electrodes. So what you could do to improve this in the future to make it a speedier reaction is to install more carbon rods. So you'd have multiple carbon rods all connected to the negative, and then you'd have multiple carbon rods all connected to the positive. You'd also have them so that they went deeper into the water as well. However, I'm not chasing speed on this. It's purely just to see what type of reaction I can get from the equipment that I've actually created. And from that, I should be able to get a good estimate of exactly how much sodium hydroxide's in the water and how much chlorine's in the water, how much hydrogen can be produced, and how much oxygen can also be produced. All right, this is the moment everyone's been waiting for, especially me. Got all the gear set up, solar panels set up, connected up to the battery pack here, and the clamps are all ready to go. Now it's just a matter of actually adding the seawater into the electrolytical cell. Once that's completed, we can put the lids on, put the balloons on, probably have to duct tape them to the vents, and then it's just a matter of connecting the system up and we'll be good to go. This should get interesting. Okay, so as you can see here, everything is good to go. We have a solar panel, back to the charge controller along the cable, back to the battery. From the battery, we're going back to a set of alligator clamps connected to a cable, back to the actual electrolytic cell itself. So positive to positive, negative to negative. Now I haven't plugged that in yet, so obviously that's the next thing to do. I've just got to connect that connection to that there, and then it will be good to go. In fact, we can probably just make a small connection there now, just to see if it's going to work. So what we want to watch is these electrodes here. They should bubble, in all seriousness, hopefully. And there we go. So you can actually see that bubbling in there. Maybe a bit hard to see, but it is doing exactly what it should be doing. And you've got to keep checking these cables, make sure they're not going to get hot. And that one there, that's starting to bubble as well. And that's what we're chasing. There are several ways that you can improve this. One of the ways, and the most effective way to improve it, which would also result in a larger power draw, is to increase the number of carbon rods in the system. So instead of just having the one carbon rod on each side, you'd have a ring of them, and you'd have them longer so they went down further into the actual water. So at the moment they're only going about halfway down there, and we could certainly improve this by going full distance, so we could go almost to the floor of the actual container itself. It's good to see that it's actually working though. That's exactly what we're chasing. It'd be interesting to get a voltmeter now and actually just check the voltage of the battery, see how many amps it's actually, or how many volts it's stabilizing that. I know yesterday I was at 13.44 while I was charging. I'm assuming it would be the same now, but with a bit of a draw on it, I'd expect it to drop back possibly to 13 or something like that, with a bit of a load on it. This stage here, not much is happening with this, although they are actually beginning to fill already. It'd be interesting to see which one fills up more. Remember, the negative side over here is actually producing sodium hydroxide and also producing the hydrogen gas from the top here, whereas this side here is producing the oxygen and the chlorine. Now there was one thing I forgot to do, so I've just had to go ahead and actually do that, which was put in the membrane in between. So we've stopped the experiment temporarily and we put the cotton wool in the bridge. So as you can see now, the fluid passes from one to the other, but there's a membrane in there to stop the chemicals from mixing as they're created. The idea of that is purely just to keep sodium hydroxide on one side and keep the chlorine on the other side. So what we can do now is we can go ahead and try again. So we'll put that back on. As you can see there, the bubbles are starting to form again. Keep in mind that as soon as I released the oxygen side over here, we lost the oxygen that had been created off the top, but never mind, we can just start again. From what I've been reading online, there's only very minute amounts of chemicals in the seawater itself, but it'd still be very interesting just to measure out exactly what quantities there are. Apparently what we can do is we can actually reduce this water here. So once I'm content that the experiment is complete, what we can do is we can reduce that water in this side here, and what will occur from that is we'll actually produce a solid form of sodium hydroxide, and it's the same form of sodium hydroxide that you can actually purchase in the cleaning aisle of your supermarket. If we can produce that, we can work out a quantity. At the moment we put in about 2.2 litres in each, so there's about 4.4 litres of fluid actually in the containers themselves, and from that we should be able to get a good idea of how much sodium hydroxide per litre. And from that we could look at producing a grand scale device. So instead of just having this tabletop device and producing our liquids and our chemicals this way, you could literally multiply this to any scale you wanted to, and from that we should be able to see exactly how many milligrams or how many grams or how many kilograms of sodium hydroxide we can produce per 1,000 litres of seawater. see the oxygen side's not quite as reactive. So that's the negative, the positive side. So all is a little more quiet on that side. However, this side, it is humming along. Now it's worth mentioning that the experiment began at 3:30 p.m. and at this stage here, the solar panels, I moved them just back over into the sun there, so we're getting full power. And as you can see here on the voltmeter, that is indeed the case. We're at 13.6667. If anything, it's decreasing slightly because the sun is disappearing, but rest assured we're getting full power into that at the moment. The only way to improve that now would be to add further carbon rods to it, which may be something I can consider doing at a later date. Thought I'd just give you a close-up of one of the electrodes doing its job. You can see all the bubbles coming off it there. So the way it works is obviously the negative current comes in at that point. It actually associates with the water, passes through the bridge, and then reconnects on the positive side with the positive electrode, which completes the circuit. So it's just a circuit of electricity going through there. Now I've just noticed something very interesting with this. See the little flakes breaking off there, floating down to the bottom? Well, that is actually the sodium hydroxide being produced. So what it's doing is it's ripping apart those molecules. Pulling apart the sodium chloride, and the chloride's remaining on one side and the sodium is remaining on this side. So those flakes that are falling down to the bottom there, that is actually the sodium hydroxide in the making. So I'm not sure if you can just, you can just see it settling on the bottom there. That's what we're chasing. There's another piece going past now. And sodium hydroxide is not cheap, and the reason it's not cheap is purely because of the way it's actually made. And the way it's made is using a lot of electricity, as you can see from here. And of course, if you want to produce it quicker, the way you do that is, again, I've said it multiple times so far, you'll have more electrodes actually in the water itself. And from what I can see of the battery, it's down to 13.66. It is certainly something that it could most certainly do. It's more than capable of doing it. There's certainly enough power there to actually perform it. However, I'm quite content just to leave it as it is at this stage. It wouldn't hurt to actually have a stirrer in there though, so something stirring the water around, and that way it's actually circulating all of the salt water around the actual electrode itself, so it's passing by the electrode, which would ensure that we're not missing any of the salt content in the water itself. I reckon that's so cool, but I'm a bit strange. It's like dandruff or snow. And we'll have a look on the other side and you won't see that. In fact, what we should see is green. It should be a green tinge to it, hopefully. So I'm hoping you can see this. I can see it with my naked eye, but at the surface of the water there's actually a color change, and it's actually tainted green or tinted green, and that is the chlorine that we've been wanting to produce. So what's always amazed me is that you can actually just go down to the beach, grab a bucket of water, purchase $10 worth of equipment, and providing you've got the knowledge, you can actually start your own chemical factory in your own backyard. In fact, if you had a little bit of financing and actually employed a real engineer and a couple of chemists to work for you, you could produce a chemical factory off the coast, or inland off the coast, I should say. And from that, you can actually generate wealth and income. So you can produce something of value out of something as ordinary as seawater, which I actually don't believe it is ordinary. I think it's absolutely fascinating, but I shouldn't say ordinary, it's as abundant as seawater. You go down to the beach and you have a look at the water, and there's not too much to be said about it. Most people look at it and feel pretty relaxed. I'm the same. However, I do look at it a little bit different. I see it as a resource. It's an abundant resource there is so much of it available that anything is possible if you put your mind to it. And as you can see here, that is very evident there now. You can actually see the tint of green to the top of the water there. So the chlorine is actually floating to the surface. Now, there's a couple of problems here with extracting this. The sodium hydroxide will be easier to remove than what will be the chlorine. And the biggest concern is I perhaps should have put a tap in the bridge there so I could actually shut the bridge off. And if I can shut the bridge off, I can lock it so that one fluid doesn't flow into the other side when I'm actually removing it. So when I tip the sodium hydroxide out of the container on that side, then I'm only getting the sodium hydroxide and I'm not getting the chlorine to flow through the bridge. See the bridge through there. It's absolutely fascinating. It's cool as. Now sadly, what I'm not seeing is the oxygen being produced. So that balloon there has got a little bit in it. You can see that it's starting to puff up a tiny amount. This one here, not so much. And the reason for that would be purely that the hydrogen is actually escaping from the device. So it's not a complete sealed unit, which is a little bit disappointing. I did test it there last night. I blew into one of these tubes here just to see if it would force the water up. It was pretty sealed. It actually forced the water through into the second chamber. However, at this stage here, it looks to be that the hydrogen is escaping, and that's fully understandable as well. Hydrogen is notoriously hard to capture. If there's tiniest cracks or anything like that in your work, it will actually escape straight out of the cracks and into the atmosphere. Now keep in mind, hydrogen is also extremely explosive. And when it goes up in a big way. It's a massive bang. For example, if it was to go off here, it would blow the top off, no dramas whatsoever. I was hoping to be able to fill one of these balloons up, but it doesn't even appear to be filling that at all. So it is escaping somewhere, which is a bit of a shame. So we may have to look at improving this at some stage by completely sealing the unit up. The only way we could seal the unit up completely is perhaps by using silicone on the lid itself. So put a bead of silicone around the top of the lid and then install the lid with everything else already in it. So all the water's already in it, the membrane's installed already as well. As you can see here, hoping that's not infiltrating onto the other side there. It looks like it may be. It's a bit disappointing. So the chlorine is actually on that side there. You can see the tint of green. Over this side here, it's a little bit of a tint of green as well, which is an indication that the chlorine's getting through the membrane. So that needs to be improved as well. I need to stuff that full of cotton wool. Now, something else worth mentioning, and a lot of people may have already picked up on this, but this is exactly how a chlorinator works in your pool. So if you've got a pool and it's a saltwater pool, you actually tip salt into your pool and then it's pumped through a chlorinator. The chlorinator is actually an electrolytic cell, and from the salt it produces chlorine, exactly what we're seeing here. So this is something that you can actually go to the shop and purchase. However, if you go to a pool shop, you're looking at like $400 for the electrolytic cell, and that's without any piping, without any casing. It's purely the electrolytic cell, which is just a series of plates, and there's no plumbing involved. You have to do all that yourself, so you're talking potentially thousands of dollars worth just to make one. Alright, something else worth mentioning is the fact that the entire process is still running at 13.6 volts. Obviously the sun's going down now, so it's going down below the house, so we're starting to lose a little bit of power here. However, it's drawing consistently off the battery and it hasn't fallen below that 13.59560 threshold, which is an indication that when it is producing power through the 200 volt solar panel over there, that this system is not using anything more than 100 to 200 volts, 200 watts of power to actually run the process. If we start to see this dramatically drop, then it's actually drawing from the battery, which is an indication that it falls somewhere below that. So I'm guessing at this stage it's possibly a 100 watt system, perhaps even less so. It's pretty stable, still sitting at 13.61 there. And from this distance here, it is very obvious. You can see the chlorine on the left-hand side one, that's the one with the red terminal, and on the other side it's pretty clear. So that's the sodium hydroxide, it's the negative side. However, we'll go and have a look at the bottom of the jar, and we should be able to see plenty of sodium hydroxide being made there now. So this is the bottom of the right-hand side jar, so that's the negative connection, and it is still snowing sodium hydroxide. It's a little sodium hydroxide factory. I look forward to actually extracting that and seeing if I can react it with some oil, so something like an olive oil perhaps, and from that we should be able to make soap. So from ocean water to soap. Now I wanted to try and explain the process with a little more clarity if possible, just so you can understand exactly what's happening, because it's a combination of chemicals in seawater. So obviously you have the water itself, which is oxygen and hydrogen, so 2 hydrogens to 1 oxygen molecule. You can use electrolysis to break apart that by itself. However, seawater is more complex than that. It also has sodium chloride in it. Now, sodium chloride, for those who may not recall from their chemistry classes back in school or whatever, is table salt. So seawater is basically salt and also O2. Sorry, not O2, H2O, which is water. So water and table salt mixed together. So when we run an electrolysis cell such as this, an electrolytical cell such as this one, what you could do is, if you wanted to break the water apart itself, so destroying the water or decomposing the water, you wouldn't need the 2 jars. You could do it out of one, and the way you do it is you'd have a positive and negative terminal in the one jar itself, and that would break apart the water by destroying or decomposing it into oxygen and hydrogen. So you'd receive both gases in equal amounts, and it'll actually break the water down. Then when you burn the hydrogen, you actually oxidize it, which you literally create water out of hydrogen gas. It's a fascinating process. So say if that balloon was to fill up completely and then I was to burn it, you actually make water. You oxidize the hydrogen, and that joins the hydrogen atoms directly back to an oxygen atom. So 2 hydrogen atoms back to an oxygen atom, and you produce liquid water. If you did it inside a case, for example, say if this jar was just empty and it had hydrogen gas in it, and you applied a spark to it, you'd actually find that water would be generated. There'd be water vapor everywhere. And in fact, I've done it once before. I had a bit of aluminium, I put it into some potassium hydroxide in a Coke bottle, I put a balloon on the top, and I didn't think anything happened. So I applied a lighter to it like an idiot and nearly blew my hand off. And inside the bottle, it was just full of moisture. So you can see the water vapor had been created. Now, with this here, because we're trying to strip it apart, we're actually producing the chlorine in one side, and we're producing the sodium hydroxide in the other. And the only reason that's occurring is purely because of this membrane here. So we're stripping apart the sodium from the chloride in this process. We're not actually stripping apart the water. So the first thing to go are the heavier molecules. So it's actually destroying the molecule of sodium chloride. So it's pulling apart the sodium, and that's blending with the water to create the snow that you can see there, which is the sodium hydroxide, which is still falling. As you can see just there, there's little white particles. And then on this side, it's obvious now, like that is getting very green. So that's actually got a high concentration of chlorine in it. And that's what we're aiming to do. You can use this procedure to do many other things with as well. So this is only one example of what can be done through an electrolytic cell. You can actually use this to make batteries as well. And the way that would work is, again, you'd have a membrane, you'd have your electrolyte, which is a fluid, and then you'd have your 2 electrodes. And from that, just by applying 2 terminals, 2 wires back to, say, an LED, you should be able to generate electricity. And you could do that out of things you could find in the bush or around your backyard. Making a battery is not all that difficult. So yeah, hopefully that gives you a better understanding of exactly what it is that's happening here. As you can see, it's still forming. I think at this stage here, I'm going to just consistently check on this, and as soon as I see that snow stop falling, it's an indication that it has actually created sodium hydroxide out of all the salt that is available in the container. And once all the salt's been consumed, there is no point continuing with the experiment. The experiment will be completed, and then I can concentrate on trying to remove the sodium hydroxide from the bottom of the jar. As you can see there, all that white material. And then I've got to work out how I'm going to remove the chlorine from the water. And apparently you can do it through a still, through distillation, very similar to what I've been doing with the seawater, distilling the seawater for drinking water and stuff like that. However, I'm yet to work out exactly when it is that chlorine evaporates. I think it evaporates well before the water will ever evaporate, so only very minute amounts of heat may have to be applied to it to actually distill pure chlorine from the water. But still completely uncertain about that, so that one we'll be learning together. It should also be noted that there is definitely a way to improve this as well. Obviously we're getting a good reaction there at the moment, but from my previous videos you may have seen that I distilled salt water. So I used an air still to desalinate water. From that I got 3.5 litres of drinking water from it, and I was left with about 150 grams of table salt. So now would be a perfect example of when I could use that table salt to my benefit. So instead of using it just to eat, obviously salt's important in the diet as well. If you had excess salt, you could turn it into sodium hydroxide. And the only way you do that is you'd have the seawater in here again, as we do now, and then you just take that table salt, that 150 grams that was produced from the desalination process, and you can just dissolve it into both of these jars here. And then in this process of electrolysis, we would break that table salt down into sodium hydroxide at the cathode and chlorine at the anode. It's a good way of using absolutely everything. Right, we are currently 5 hours in, so almost 5 hours, 4 hours and 50 minutes into the experiment, and it's been running off just battery power at the moment, so we're down to 12.66. In this container here, you can actually still see that there is a reaction going on at the carbon rod there, so it's still bubbling. And there is a massive buildup of sodium hydroxide in the bottom here. So that's after 4 hours, 50 minutes. It's about half an inch, even an inch thick in places around the bottom there. So I look forward to removing that. That will be a job for tomorrow though, of course. And then of course, this one over here still tainted green, so we're still producing chlorine at the anode. But not quite as heavily as what we were. You just see that it's still bubbling. So I think we're probably best just to leave it run all night. Still plenty of power there, so see how it goes in the morning. Alright, it is now about 6:10 the following day. I've still got 12.6 volts left in the battery, so we haven't run out of energy. There's still plenty of energy there. However, the bubbles have stopped flowing from the electrodes. So that there is an indication that sometime during the night, the salt has actually run out of these devices and it has converted all of the salts into either sodium or into chlorine. Now I've had a chance to do a bit more research into whether this is indeed sodium hydroxide,
from everything I've read, there's an indication that it should be. However, there is a possibility, because I use carbon rods as the cathode and as the anode, that the carbon has actually reacted with the sodium and produced nitrite. It's called natrum. It's actually what the Egyptians used to use to mummify their dead in ancient Egypt. But there's only one way to find out whether that is the case. From everything I've read, it should be sodium hydroxide. However, it could be sodium carbonate or nitrite, sorry. And there's only one way to find out, and that's to actually go ahead now, take this inside, dismantle it, and separate the liquids. I think to do that, I'm actually going to have to get a Coke lid, so a Coca-Cola lid, and actually insert it in each end of that bridge to plug it up, and then I should be able to tip it out into 2 separate bowls. And that way I've got 2 separate forms of the liquid. And that's it. Alright, now I just want to do a couple of final observations before I actually go ahead and pour the contents of the electrolytic cell into these bottles here. So one is the fact that the carbon anode on the positive side here is actually disintegrating. So it's starting to break down, and that's purely because of the corrosive environment of the chlorine that's been created on that side there as well. Another point worth mentioning is the fact that that's not quite as green as what it was yesterday. There's still obviously there's an obvious color difference there. However, it's not as green as it was yesterday. So whether that's because it's reduced its chlorine content during the night, because I've left it too long, I'm not too sure. And a third point worth mentioning is that this is indeed an electrolytic cell. So even when it's not connected to electricity, because of the electrical difference between these 2 substances here, it should generate a current of electricity. And we can prove that by just simply connecting up our alligator clamps back to our voltmeter here, and then measuring how many volts it's actually putting out. Now, the average cell from a battery should produce 1.5 volts. This is producing 1.3, which shows that it is a working electrical cell. You would need to set up, I believe it is 6 or 7 of these to actually produce enough electricity to produce 12 volts. So anything you're powering with a 12 volt device, you could potentially do it with some electrolytic cells such as these. You'd set it up to harness the 12 volts first, and then after doing the 12 volts, so 1.5 plus 1.5 is 3, so you'd need 8 of them. If you've got the 8 of the cells, you may have enough to generate the 12 volts, and then it's just a matter of not only connecting it in series, which is adding it up to get to the 12 volts, you would then go ahead and add it in parallel, and doing the circuitry in parallel increases the ampage. So not only are you getting 12 volts, but then you're getting an increase in the amp. And theoretically, you should be able to make enough of these jars to jumpstart your car. No joke. It's awesome. So at this stage, at least we've recorded all that information. So it's all there for everyone to see. And what I'll do now is I'll go ahead and I'll see if I can pour these out. Now I'm doing this outside because that's chlorine gas and you can smell it. So it's obvious that that's chlorine in there, and there will be a bit of chlorine gas on the surface as well. The balloons failed to do anything, so they're doing absolutely nothing. This one here's got a little bit of pressure in it, next to nothing though, so most of the hydrogen's escaped, most of the oxygen's escaped. That has failed to work. However, I have been doing a bit more research into other ways to do this, and I have come across an idea that will be worth doing for our next electrolytic cell. And that way we can collect all the hydrogen gas and all the oxygen as well. At this stage, we'll go ahead and we'll collect those 2 substances. So we're just going to go ahead here, take this lid off. So, oh man, that is strong. If I'd stuck my head in any further there, I probably would have gone down like a big sack of crap. That is strong. That is extremely strong chlorine solution in there. It nearly blew my head off. Would have made for great viewing with my head hitting the table just here, but so it's mainly the chlorine gas that's just escaped. So you can still smell that there is chlorine in that, so that's very good. That's exactly what we're trying to achieve. I'm going to actually try and use these caps to plug the bridge up in here, so I'm going to go ahead and do that now. I will be putting my hand into the substance. And that's not going to work. Alright, so I've just gone ahead, used a bit of duct tape to actually block that up, and that way I can remove the chlorine liquid from it. In fact, I'll probably do it in portions, so I'll take some chlorine from this side and then I'll take some sodium hydroxide from that side. That way the levels fall together and it's not going to siphon one off into the other. We don't want the sodium hydroxide being siphoned off into the chlorine. We don't want chlorine being siphoned off into the sodium hydroxide either. Now I've just removed the top of the sodium hydroxide side, and at this stage it has no chlorine smell at all, which means very little chlorine has actually made it through to the other side. So we'll continue to siphon that off. I think the best we can actually hope for is just to do one side to the other. So now we go back into the chlorine side, lower this side, and into the sodium hydroxide. So I guess in the future we could design it so that the bridge acts as a switch. So it'd be a good idea to put a tap in there, that way we can isolate both sides from each other, so the sodium hydroxide from the chlorine and vice versa. But for the time being, this is what we've got, so this is what we've got to work with, and it is working. It's just not quite as professional as any other way, but this is backyard science. It's what you get. Thinking there before, when I lifted the lid off the chlorine as well, I could have actually, if I could have isolated either container and dismantled them, I could shake that container up, and what that would do is it would actually infuse the chlorine gas from the surface of the container actually back into the fluid, and that would give us a richer chlorine in the water, or a richer form of chlorine in the water. See the difference in the fluids. Obviously this one here, very pasty white, chalky white even. That one has still got the tinge of green to it. It's interesting, I used to work with chlorine quite a bit, hypochlorite. We used to clean a lot of cutting boards and that at a butcher shop, so the smell has always reminded me of the butcher shop. And we got up to some mischief in there. Using hypochlorite, you mix it with preservative. This is 25 years ago in the drains, and it used to basically combust into a smoke, and the whole shop would have to be evacuated. I never did it, but I watched people do it and got asked to evacuate when they did it. Crash course chemistry by a bunch of hillbilly butchers. Righto, so we got 1.25 of each of them at this stage. We'll continue on and we'll see exactly how much fluid we got. We did lose a little bit out of this one as well. Obviously when I put my hand in there to try and block it up, a little bit overflowed, but that's the way it goes. Right, the only way to get the remainder of this out without causing too many dramas is to actually just tip both of them up into separate containers at the same time. like so. We're going to want to get all this out of here as well. That's all either natron or sodium hydroxide. Might even just give it a swirl. Chlorine side is spotless. Whoa, and it is strong. I'm just surprised at how well it worked. Obviously, it's a well-tested experiment. It should have worked. I'm just happy that it did work. Took this up into here. If you have a look at that there, that should be the sodium hydroxide, and if you run your fingers through it, you can actually feel that it's very soapy, and that's exactly what it is. It basically hydrolyzes the fats in your skin to create soap, which is exactly the reason why they use fats in Fight Club, for example, to make soaps and other mischief. Now what I've noticed is we're missing quite a bit of fluid here. So I was under the impression that I put 2.2 litres into each. However, at this stage it's falling below that. So I'm going to have to go back and put some fluid back into these cells just to find out exactly how many litres I put into it. It's the problem when you try to do things afterwards. You just can't be sure of exactly what it is we put in there in the first place. Now we must be pretty close. But at this stage here you can see we've got 1.2, it must be nearly 2 litres of chlorine and slightly less of the hydroxide, which is really, really odd. If anything, that's an indication that some of the hydroxide has gotten through to the chlorine side, but anyway, I guess we might even do a quick measurement directly into this Pyrex here. We've got 2 litre marks on here. It's a really good way of finding out exactly how many litres we actually have in there. So we'll do that now. Keep in mind, each time we pull these through, we lose some of the chlorine gas from it, which is a bit of a shame, but we want to get it right, so we'll do the measurement. Oh, each time I do that, I'm surprised at exactly how strong that chlorine is. Trying to undo bottles one-handed, that's always entertaining too. So we are at a little over 2 litres there for the chlorine. It's a good opportunity to measure out the hydroxide. We're just shy of 2 litres. That's sodium hydroxide solution. Now if we want to remove the actual sodium hydroxide from it, we have to evaporate the water off, which means running it through the still. And I actually plan on doing that as well. Should be interesting. Then I can test to see whether it's actually sodium hydroxide or natron. If it's natron, pretty limited with its uses. Sodium carbonate. If it's sodium bicarbonate, obviously you can use it for many different things. You can use it for cooking, for example. If it's sodium hydroxide, that's what I'm really interested in. I want to see if I can use it to make soap with. Something I've been trying to achieve for years. Okay, so that's the conclusion of the experiment up to this point. So we know for a fact that we definitely got the chlorine from it, which is in this bottle here. These bottles, sorry. So there's a little bit over 2 litres of chlorine, or chlorine solution. How to enrich that, that's another question for another time. And then our sodium we've produced here. So there's a clear difference between the two. You can see one's pale green, one's cloudy white. Both of these are cleaning solutions. So if you have a look at my hands, they are pink, purely just because I've been working with it and haven't been using gloves. Chemist teachers would just absolutely love that, I'm sure. But I've worked with chlorine my whole life basically, and been in enclosed spaces with it and stuff like that. I've learnt thresholds. That's still no excuse. You should probably wear respirators and gloves and all that kind of thing, but you shouldn't be afraid to have a go either. Obviously you don't want to go sticking your head in there or hawking that bit of gas out of there, for instance. That there would be highly toxic, but as long as you do it out in the open, everything should be sweet. Now this here, what I'll be aiming to do is reducing it. So that's the next stage. I will do a couple of minor experiments with the fluid as well, just to see if it will react with an oil, so an olive oil for example, to see if it will hydrolyze it. If I can get it to hydrolyze it, we may be able to make a liquid soap, just as it is, without having to evaporate the water off it. However, part of the experiment was to see how many grams of sodium hydroxide I could actually remove from it. And then I can test to see whether it is actually sodium hydroxide as well, and not just natrum or nitrum, sorry, yeah, one or the other anyway. So for now, that's pretty much everything. What I will do is I will conclude this video at this point. It's already dragged on for over an hour and 10 minutes, or an hour and 15 minutes even perhaps. But the idea is all the information is there. You've seen pretty much every step of the process, including how to actually build the H cell itself. You've also heard all my suggestions on how to make it better. You have heard that I plan on actually capturing the gases, so the oxygen and the hydrogen gases, in another fashion, in another design that I'm yet to do. At this stage, obviously the gases escaped somehow from these lids here, which is understandable. You're talking, I think they were like $4 containers from Kmart, so not a lot of money was spent in actually manufacturing it, but that's the idea, is to show you exactly how little money you can actually spend to produce items of value. If you can go about doing this, you can literally, like I was saying earlier in the video, you could set up a mini chemistry industry, a localized industry. Because you've got to remember, all these chemicals, they come from somewhere. So whenever you go to the shop and you buy it for floor cleaner, or you go and buy soap, it has to be transported. And a lot of the time, sodium hydroxide and the chlorine, they're produced in factories in possibly other countries. So they're actually put on ships, and fuel is used to actually get them here. Fuel is used to produce them. I produce this by literally going to the beach with my family, getting a bucket of salt water that I didn't use all of, we only used a tiny amount, came home, hooked it up to a solar panel and an old car battery that should have gone to the dump. And I produce these chemicals with the smallest carbon footprint imaginable. It's just evidence that there is no doubt in my mind that we are certainly going about things the wrong way. You know, why couldn't you have a localized chemistry industry in my hometown on the coast here, for example, or in your hometown on the coast? It's not impossible. It's purely all about knowledge, and if you've got the knowledge on how to do it and you meet all the government requirements, sadly, but that's the beauty of a disruptive industry, is you just do it. Just go out and do it and produce the items of value. Like these here, we could literally take this to a market, for example, and sell them over the counter at a market. And I know you're talking about legal thresholds, and perhaps it's not quite legal doing that. Well, why not? Why isn't it? You can sell soap at the market. I'm sure you should be able to sell the basic components of soap as well. And you can go to your supermarket and buy chlorine, and because it's got a warning label on it not to drink it, then that's legal. Yet if you go to sell it at a market, then there's a problem. Yeah, welcome to 2022, and things have got to change.